Hello, this is Unit 3, Topic 4, Sampling Distributions and the Central Limit Theorem. So in this topic, we're actually going to look at a few things that are going to seem kind of vague and abstract, but they're going to boil down to two very specific concepts towards the end. I do feel as if it is worth it to go through these ideas rather than just have the two rules given to you. I would consider it to be slightly irresponsible to just say, here are these two rules and not give you any background as to why. So we will go on in a journey, an exploration, if you would. So first of all, in the previous topic, we looked at items and situations that followed the normal distribution, but we only sampled one person or item from those distributions. So the first example from topic 3 was an owner of a buffet restaurant found that the mean amount that customers ate was 878 with a standard deviation of 112. We did two things, and a few more actually, but we found the probability that a single randomly selected customer cost the restaurant between 766 and 990, and we also found the probability that a single randomly selected customer cost the restaurant less than $7. So what happens when we select more than one is the question that's going to come up. So after, we were given the previous questions and we used the z-score formula, we used a mean of 878 and a standard deviation of 112. But if we sampled two or more customers, can we still use that same population mean and standard deviation sigma? Well, first instinct usually says, well, yeah, that's the mean and standard deviation. But that's actually not the case. So I have two images down here with a number of question marks on the right side. But on the left, we have our population, the same exact scenario that we've been discussing. The mean of this one person, we use 878 and 112. However, if we select two people, or we're going to extend this to more than two people, does this end up being the same? And the answer is no, they don't end up being the same. So there is a certain way that they change. I could just tell you why, but we're going to spend a little bit of time exploring this because it contains a few ideas that are kind of central to statistics. You'll see pun intended on that statement. So to do this, we're going to need to look at sampling distributions. Sampling distributions in themselves seem kind of unrealistic, and it's because they are, but we need those in order to get down to the theory of statistics. So a sampling distribution of a population is the probability distribution of a specific statistic for all samples that can be made of a certain sample size. So we're going to make one of these. Specifically, the sampling distribution of the mean is the probability distribution for all values that are a sample size n, all values of the mean resulting from that sample. So like I said, this is extremely vague, and when we do an exact example, it will make a lot more sense, but it is still kind of out there. So without further ado, let's go back to our very familiar situation of rolling a dice, or a die. So if we roll a die, the outcome are 1, 2, 3, 4, 5, or 6. So let's make the sampling distribution for all possible rolls of 2. So 2 rolls in a row. So to do this, we're first going to need to make the sample space. Sample space, remember, is just a description of all possible outcomes. So the sample space in this is going to have 36 total elements, and it's going to be 1, 1 all the way up to 6, 6. Excuse me. So make sure that this makes sense to you. The sample space isn't the number, it's just what each of those are. So it's a description of all possible outcomes. So then from here, in order to make the sampling distribution, I have this lovely table in here. And so what we're going to do is we're going to find the mean and standard deviation for each of these samples. So you're going to do this in Stata, just the way that you found the mean of any other data set here. So the way that I've set this up is I have all of the possible samples of size 2 in these columns, and then that's a little spacer. So, and then we're going to find the mean and standard deviation of each of these samples. Well, what you will do eventually, if you did do this on your own, is you'll find that the mean of I always start with the pairs. So 1, 1 has a mean of 1 and a standard deviation of 0. The mean is the middle number, and in this case 1 and 1, they are both the same, so there's no middle number. And the standard deviation tells us about how much do the values deviate from the mean. And in this case, our values don't deviate from the mean at all. They're exactly the same. So we'll find that this with a similar extension will go on for all the pairs. So 2, 2 has a mean of 2, a standard deviation of 0. 3, 3 has a mean of 3, a standard deviation of 0, all the way up to 6, 6, which has a mean of 6 and a standard deviation of 0. So in order to find these standard deviations, I would probably find the means in my head. But let's not make any assumptions here. Whoops, my Stata has disappeared into the nethers. So this is actually a good time to remind you that Stata doesn't like to come up when you do a search on your computer. So you need to actually go into where your computer saves your files, which unless you have a Mac is going to be your Program 86 folder. So if we wanted to find the standard deviation of 1 and 2, let's say, I would go to get a data editor, and I would just want to put 1 and 2 here. And then we can use the plain old descriptive statistics that come in the original data editor. But in general, doesn't give us very much information. So let's see. Yeah, we don't have a variable name. There we go. So when we hit OK, there's our mean of 1.5 and our standard deviation of 0.707. Now, you might say, how in the heck can you expect us to find this many standard deviations? Well, if you look carefully here, there's going to be lots of repeats. So for example, 0.707 is for 1 and 2, but it's also going to be for 2 and 1 as well, because on average, the values deviate from the mean in the same exact way. This is going to be true every time that your values are 1 apart. So for example, 2, 3, they differ from the mean by a half above and a half below. So there's going to be lots and lots of repeats for your standard deviations. This is actually an exercise that I would recommend doing. So I would go back and I would start finding these in their repeats if you didn't, because it's going to give you a really good idea of how means work, how standard deviations work. I know we're familiar with both of these concepts, but it will get you familiar with them on a slightly deeper level. But anyway, this is the work on the back end. What ends up coming from this is the probability distribution for the population. So we have outcomes 1, 2, 3, 4, 5, and 6, and they're each equally as likely. Now, I know that we're rolling 2 dice, but they're each going to be equally as likely. So that's not something that we keep into account here. So we're just looking at, what are our outcomes and how likely are they to occur. So this is a nice flat kind of distribution here. They're all equally as likely. Uniform distribution we talked about, this would be a discrete version of it. Next, we have the sampling distribution for the mean. So our mean values go from 1, they go up halves all the way to 6. So there's only 1, 1, and there's only 1, 6. But there's a few repeats for some of these other values. So what I would do is actually count. Okay, how many 1s are there out of a total of 36? How many 1.5s are there out of a total? So there'd be 1 and 2 would have a mean of 1.5, and so would 2 and 1. So when we plot these, we end up getting this pointy shape. Is it bell-shaped? Well, it's not bell-shaped, but it doesn't really have a curve to it like the bell shape does, but it's not really far away from looking bell-shaped. And then lastly, our sampling distribution for the standard deviation. So here we have these 6 standard deviations that occurred from the values being none apart, so they were 1, 1, 2, 2, all the way up to 5 apart. So 1, 5, and 6, and 1 and 6, and 6 and 1. Both of those values were 5 apart. So those had 2 out of 36 of those were 0.0556. So just to clarify, there's 36 total outcomes here, and there are 2 standard deviations that are 3.536. So we've got the one here for 1, 6 and one here for 6, 1. So this is 2 out of 36, which is where that 0.05 repeating comes from. And on this chart, it's actually, no thank you, I won't rate you. So it's actually rounded up. So the other thing I'd like to comment on is that this has a skewed right kind of shape. The shape that these make are actually really important. It seems like, hey, this is just kind of, like a line graph, but the shape that these make are actually really important when it comes down to some fundamental ideas of statistics. So what does this mean for our lives? Well, here are our 3 sampling distributions. And the population has a mean of 3.5 and a standard deviation of 1.708. The mean, so this is the mean of all the means basically, given how much they weigh. The mean of all those means is 3.5. And at this point, I wouldn't follow me with actually finding the means and standard deviations. There will be a video to follow that will address this specifically. But for now, you are not responsible for this in any way whatsoever. Standard deviation, you're actually going to find a mean of these because these are all of our standard deviations. We don't want to find out how the standard deviation of how much they deviate. We just want to find what is one number to summarize all the standard deviations. So what ends up happening is that this 1.375 is different from 1.708. But the mean, 3.5, is the same as the original 3.5 mean over here. So to answer the original question, can we still use the same mean and standard deviation if we sample 2 customers? Well, not quite. We can use the mean. So the mean of the population and the mean of the sample are always going to be exactly the same no matter what your sample size. However, the standard deviation changes. So all of this boiled down to that concept. If you are taking a sample from some population, the mean of the sample stays the same as the mean of the population, but the standard deviation of the sample is different than the standard deviation of the population. This is really important. We'll see some examples and it will make more sense why this is so critical. Oop, check mark and an X. So let's repeat this, but with a smaller example. So I'm going to actually just leave this here. There will be a video later on as to how to actually calculate these. But this is if you wanted to try one on your own. But at this time, I don't expect you to do one on your own. Setting up these tables would be something I would recommend being able to do, but finding these mean and standard deviations, I actually decided to separate into its own video. So, beyond a sample size of 2, let's go back to rolling the dice twice. But let's extend this to now rolling the dice 3, 4, 5, and 6 times. So what we'll find is that the mean will always stay the same. So I basically did the sampling distributions separately and then found the mean and standard deviation here. Specifically, the standard deviation not only changes from one sample size to the next, but it's getting smaller. So what we will find is that when we are selecting a sample with mean, mu, and standard deviation sigma, the mean of the sample is the same as the mean of the population. So we saw that a number of times. The standard deviation of the sample is different from the the standard deviation of the sample is different from the population standard deviation. Specifically, it is the population standard deviation divided by the square root of the sample size. So whenever we're selecting more than one, our mean will stay the same as the population, but our standard deviation will make a change. So this all boils down to the central limit theorem. The central limit theorem has two components. First, even if the distribution of the population is unknown or is known and it's not normally distributed, as long as we have a big enough sample, we will be using at least 30 as our big sample. The normal distribution will still apply. So this is actually huge. It says that you can collect data, and as long as you have randomly selected it, if you have a big enough sample, you can still use normal distribution rules anyway. Next is that for a sample that is normally distributed or that the central limit theorem applies, meaning that we have treated it as being normally distributed, we can use the same mean for the population as the sample mean, and the sample standard deviation will be sigma divided by the square root of the sample size. So we did a lot of stuff to boil down to these two items. We're going to look at one more thing, which will help demonstrate this idea. Oops, looks like I lost my link. So we're going to look at an applet that's going to show kind of what the central limit theorem actually means in a more visual sense. So this will be up on your main page for your links, as well as within your section for this. So this applet takes a population, which we're going to start at as normally distributed, and it looks at what happens if we make a sample size of 5 and finds the mean of each of those samples. So let's animate it for funsies. So what it first does is it selects 5 random numbers from this overall distribution, and it finds the mean here. And so we can do it again. And then we can have it do 100,000 at a time. Well, what happens is, and you can have it do, every time it's doing 100,000, look at this is how many samples of 5 it's found, and then found the mean for it. So even though we only have a sample size of 5, this sampling distribution ends up being normally distributed looking pretty quickly. Now the other thing is that the mean of the sample is exactly the same as the mean of the population. However, the standard deviation has changed. So let's, this is something I'm going to have to do in my regular calculator. I don't think my computer calculator is going to do good enough here. So what I'm entering in is the population standard deviation of 5 divided by the square root of our number of reps here. Oops, so this is going to be off, but, for a sample size of 5, I'm sorry. 5 divided by the square root of 5. So that's where we end up getting the 2.24 that this has come up with. So let's try this again. And then obviously if we make our sample bigger, it's going to be normally distributed as well. And it's going to be a little bit more compact because the new standard deviation is the old standard deviation divided by the square root. The old standard deviation divided by the square root of the sample size, which would now be 25. So the bigger the sample size, the tighter our curve becomes. So you see each time it does a sample, 100,000 samples and their means. Now, the uniform distribution is also quite well behaved. So if we do a sample size of just 5, I'm not going to animate it, I'm just going to, wow. So even with a sample size of just 5, we end up having this beautiful bell curve shape. If we increase it, so even though our original population was, a big brick, our data, the means of those ends up being a bell curve. So the central limit theorem gives us so many liberties that we're able to take, and it is very well proven. All right, so let's see how much more narrow that gets. Yeah, pretty narrow. So let's look at one that isn't as pretty. This is a skewed distribution. I'm going to start again with a sample size. Let's start at 2. So originally, when you have those samples made, you end up getting a shape that sort of retains the same shape as this parent population here. So our bell curve shape is not awful, but it's still definitely skewed right. As we increase in sample size, we still have a skewed shape, but it is getting better looking. Okay, so let's jump to 25 here. Wow, and then we have a nice pretty bell curve shape. So when we take a sample of 25 100,000 times and finds the means of each of those 100,000 samples and we plot them, even though this original curve isn't bell-shaped, we end up getting a bell shape down here. So it's kind of hard to understand how, I don't know, magical this is. But to me, as far as I'm concerned, this is basically black magic. So let's do the custom, and we'll fill in our own population here. Let's make it look like this. So now this is a pretty unique population. Our values are falling at the very low end and the very high end. Our mean is still obviously smack dab in the center, but the median is falling way down over here. So I'm going to find a sample size of 2, 100,000 iterations, and that gets us this. Okay, so it looks like sometimes all of those two numbers happen to be in the low end. Sometimes they happen to be on the high end, and sometimes the one from each. As we increase the sample size, we start to end up falling into the normal distribution. As far as I'm concerned, this is seriously magical, because this means that we can use the normal distribution no matter what it looks like as long as our sample size is big enough. Now, a big sample, which is what we're calling to be 30, is not a hard cutoff. It's very rough. It's not solid. So for example, 25 is not quite 30, but we still kind of have here this is be bimodal, 2 modes. Here we end up getting something, that's sort of normal shaped-ish. So it's not completely horrible. The mean is exactly the same, however. Standard deviation, let's see how that compares. So I've never seen this distribution before. So I'm doing 15.35 divided by the square root of our sample size of 25. So it still works out even though it's not quite a bell shape. So regardless of what your distribution looks like, the parent distribution, you can still use the normal distribution as long as you have a sample size of at least 30 as our cutoff. So this isn't quite pretty enough. And you can play with this. You can do whatever you want. Let's see what that one looks like. That one's not great, but not bad either. It still maintains that original shape. There are some distributions that no matter how big your sample size is, you will always end up getting nothing that looks like the normal distribution. So we're going to look at one more thing. So I'm going to type in bootstrapping Excel. And this is going to show why we don't do anything with the median as far as beyond descriptive statistics. So this is an example of bootstrapping, which is a pretty cool concept in statistics, but it is kind of vague, so I guess join the club for the rest of things in this topic. So what this data is this is real data. This is from the department chair of the statistics department at University of Wyoming. And this data represents 1 divided by a distance. And the distance that he was using is the distance between fire ant hills. So what bootstrapping does is it takes a sample of 25 from this with replacement. So it randomly selects a number, it puts that number back. It randomly selects another number, and then it puts it back. It can be the same number. So for example, I could select this 13.835 10 times. Probably not going to happen. But and then what it does is it computes whatever statistic you're interested in. So look at how disgusting this distribution is. This would be like the custom example I just did with the applet. So when you do a bootstrap, it finds 1,000 means and plots them. So even though this distribution was absolutely positively disgusting, we had a nice bell curve shape come out. And this again is doing a sample size of 25 just because it kind of ends up being easier in the technology end. So nice, pretty bell curve. Let's do another 1,000 samples. Oh, it's so pretty. And you have to remember that every time I click this button, it's finding 1,000 samples. It's finding the mean of each sample, it's putting it in this histogram, and it's doing these other calculations over here. Which, if you don't think that's impressive, then I don't know. I don't know how to impress you then. So standard deviation is pretty similar. They're all going to be pretty bell-shaped. This is for a reason that we will learn in topic 5. So they're bell-shaped, curved-ish. Now, the median is our sort of our arch enemy. The median, again, I don't know if I used this analogy in the original video, but let's say you need a babysitter. And you have 2 babysitters you use, and one is really reliable, but your kid doesn't find the babysitter to be very entertaining, but they're always going to show up. Whereas you have this other babysitter where, they're super fun and they play lots of games and they read books and the kid just loves this babysitter, but they're really super unreliable. Well, unfortunately, if it's planning that you can't have a mess up, you're going to want to select the one that's really reliable. Well, let's look at what the median does. So when we find 1,000 samples, the median behaves like this. So this isn't a pattern that we can really pin down. And not only that, is it's not always the same. It varies between these two pretty common ones, but it's definitely pretty weird looking over time. So this is why in the future we're not going to use the median, but we are going to use the mean and standard deviation pretty frequently because they are very reliable, which is extremely important when it comes to statistics. So a lot of what we talked about in this topic was very vague. I understand this. In the next lab activity, you will be asked to do a sampling distribution, but I will have a video along with it. If you are going through the video now and you really desire to do that example with the 1, 5, and 10 packages, which is the one that I skipped, please feel free to send me an email. But for the most part, I ask that you remember 2 things. And the 2 things are the central limit theorem, the last final slide. So I know we did a lot to get there, but a lot of these things are very central to statistics. So even though it might not make it to a quiz or test, it's something as a person that I want you to know leaving this stats class. So if you have any questions, as always, please send me an email.